National Electrical Code, NEC, does place limitations on 480-volt services. It's often stated that the NEC limits 480-volt services to 700 amps per phase. This is generally tied to the common availability and ampacity ratings of the largest readily available wire size, specifically 750 kc mil copper conductors with THHN insulation. A 750 kc mil THHN copper wire typically has an ampacity of 700 amps when installed under normal conditions, as per NEC Table 310.15b16, formerly Table 310.16. However, it's crucial to understand that the 700 amp limit is not an absolute ceiling, and the NEC provides allowances for exceeding it under specific circumstances. The key is to carefully examine the applicable NEC articles and tables to determine the allowable ampacity for a given installation. One important consideration is the installation method. If the service conductors are installed in a raceway, such as conduit, the ampacity of the wire may be increased based on the full percentage of the raceway and the ambient temperature. NEC Section 310.15c provides adjustment factors for more than 3 current-carrying conductors in a raceway or cable. These adjustment factors reduce the allowable ampacity of the conductors. The NEC provides tables for ampacity correction factors based on ambient temperature in Section 310.15 bone. For example, if the ambient temperature is higher than 30 degrees Celsius, 86 degrees Fahrenheit, the ampacity of the conductor must be derated. Conversely, if the service is installed in a cold location, the NEC may allow for an increase in the ampacity of the wire. However, this is not a straightforward 10% increase, as it depends on specific conditions and NEC allowances. NEC Section 310.15 outlines the requirements for conductor ampacity and temperature correction and adjustment factors. It's imperative to consult the specific NEC tables and sections relevant to the installation conditions. To meet the 1100 amp requirement for the 480 volt service feeding the pumps and other loads, several strategies can be employed. Firstly, using multiple sets of conductors in parallel is a viable option. The NEC permits conductors to be connected in parallel under certain conditions, as outlined in Section 310.10h. When using parallel conductors, all of the following conditions must be met. Firstly, the conductors must be the same length. Secondly, the conductors must be of the same material. Thirdly, the conductors must be the same size and circular mil area. Fourthly, the conductors must have the same insulation type. And fifthly, the conductors must be terminated in the same manner. By running multiple sets of adequately sized conductors in parallel, the overall ampacity of the service can be increased to meet the required 1100 amps. For instance, 2 sets of 750 kc mil THHN conductors in parallel would provide a combined ampacity of 1400 amps, which exceeds the 1100 amp requirement even before considering any potential derating or adjustment factors. Secondly, larger conductor sizes beyond 750 kc mil may be available, although they are less common. Some manufacturers offer conductors up to 2000 kc mil. The ampacity of these larger conductors can be found in the NEC tables. Thirdly, optimizing the installation method to minimize derating factors is essential. This includes ensuring adequate ventilation around the conductors and raceways to prevent overheating, and minimizing the number of conductors bundled together in the same raceway. Fourthly, using conductors with a higher temperature rating, such as THHN/THWN-2, which are rated for 90 degrees Celsius in dry locations, can allow for a higher ampacity compared to conductors with a lower temperature rating. However, the termination equipment must also be rated for the higher temperature. In the specific scenario described, where the load includes 2 350 horsepower pumps running simultaneously plus other loads, it's essential to perform a comprehensive load calculation to determine the actual service amperage requirement. This load calculation must consider the nameplate ratings of the pumps, the starting currents of the pumps, and the demand factors for the other loads. The NEC provides guidelines for calculating motor loads in Article 430. The service entrance equipment, including the overcurrent protection devices and conductors, must be sized to handle the calculated load. If the calculated load exceeds the allowable ampacity of a 480 volts service, even after considering the aforementioned strategies, a high voltage service may be necessary. The two standard motor voltages above 480 volts are 2300 volts and 4160 volts, not 575 volts as was suggested. These higher voltages can reduce the current requirements for the same amount of power. If a higher voltage service is chosen, a step-down transformer will be required to provide 480 volts for the pumps and other loads. The transformer must be sized to handle the total load connected to it. The transformer's kilovolt ampere kVA rating must be greater than or equal to the calculated load in volt amperes. The kVA rating of the transformer can be calculated using the following formula: kVA equals volts times amps divided by 1000. The selection of the appropriate transformer voltage ratio depends on the available utility voltage and the desired output voltage. For example, if the available utility voltage is 2300 volts, a 2300 volts to 480 volt step-down transformer would be required. The transformer must be installed in accordance with NEC Article 450. This includes requirements for ventilation, overcurrent protection, and grounding. In summary, while the NEC often refers to a 700 amp limit for 480 volt services, this is not an absolute restriction. The allowable ampacity depends on several factors, including the wire size, insulation type, installation method, and ambient temperature. By carefully considering these factors and utilizing strategies such as parallel conductors, larger conductor sizes, and optimized installation methods, it may be possible to meet the 1100 amp requirement with a 480 volt service. However, if these strategies are not sufficient, a higher voltage service with a step-down transformer may be necessary. It's always recommended to consult with a qualified electrical engineer or contractor to ensure that the electrical service is designed and installed in accordance with the NEC and all applicable local codes. Now, let's delve into some specific NEC sections that are particularly relevant to determining the maximum service amperage allowed for a 480 volts three-phase service. We've already mentioned NEC section 310.15. which is the cornerstone for understanding conductor ampacity. This section provides the ampacity tables for various conductor sizes and insulation types, such as THHN, THWN, and XHHW. These tables list the allowable ampacity for conductors based on their insulation temperature rating and the ambient temperature. However, it's crucial to understand that the ampacity values listed in these tables are only applicable under specific conditions. NEC section 310.15b3 addresses a situation where there are more than 3 current carrying conductors in a raceway or cable. In this case, the ampacity of the conductors must be derated according to the adjustment factors provided in table 310.15 cone. The derating factors are based on the number of current carrying conductors and the ambient temperature. For example, if there are 4 to 6 current carrying conductors in a raceway, the ampacity of the conductors must be derated to 80% of the value listed in the ampacity tables. This derating is necessary to prevent overheating of the conductors. NEC section 310.15b2 addresses the situation where the ambient temperature is higher or lower than the reference temperature listed in the ampacity tables. The ampacity of the conductors must be corrected using the correction factors provided in table 310.15 burn. For example, if the ambient temperature is higher than 30 degrees Celsius, 86 degrees Fahrenheit, the ampacity of the conductors must be derated. If the ambient temperature is lower than 30 degrees Celsius, the ampacity of the conductors may be increased, but only up to the maximum temperature rating of the conductor. NEC section 310.10h provides the requirements for conductors connected in parallel. As previously mentioned, conductors can be connected in parallel to increase the overall ampacity of a circuit. However, several conditions must be met for conductors to be connected in parallel. Firstly, all of the parallel conductors must be the same length. Secondly, all of the parallel conductors must be of the same material. Thirdly, all of the parallel conductors must be the same size in circular mil area. Fourthly, all of the parallel conductors must have the same insulation type. And fifthly, all of the parallel conductors must be terminated in the same manner. NEC Article 230 covers service entrances. This article provides the requirements for the service conductors, service equipment, and overcurrent protection devices. NEC Section 230.42 specifies the minimum size of the service entrance conductors. The service entrance conductors must be sized to carry the calculated load, but in no case shall they be smaller than required by the NEC tables. NEC Section 230.90 specifies the requirements for service overcurrent protection. The service overcurrent protection device must be sized to protect the service entrance conductors from overload and short circuit. The overcurrent protection device must be located at the service entrance and must be readily accessible. NEC Article 430 covers motors and motor circuits. This article provides the requirements for motor conductors, motor overload protection, and motor short circuit protection. NEC Section 430.22 specifies the minimum size of the motor conductors. The motor conductors must be sized to carry the motor full load current as listed in the NEC tables. NEC Section 430.32 specifies the requirements for motor overload protection. The motor overload protection device must be sized to protect the motor from overload. The overload protection device may be a thermal overload relay, an electronic overload relay, or a circuit breaker. NEC Section 430.52 specifies the requirements for motor short circuit protection. The motor short circuit protection device must be sized to protect the motor and the motor conductors from short circuit. The short circuit protection device may be a circuit breaker or fuses. NEC Article 450 covers transformers. This article provides the requirements for transformer installation, overcurrent protection, and grounding. NEC Section 450.3 specifies the requirements for transformer overcurrent protection. The transformer overcurrent protection device must be sized to protect the transformer from overload and short circuit. The overcurrent protection device must be located on the primary and secondary sides of the transformer. In summary, determining the maximum service amperage allowed for a 480 volts, three-phase service requires a careful review of the NEC. The ampacity tables in NEC Section 310.15 provide the starting point for determining the allowable ampacity of the service entrance conductors. However, it's crucial to consider the dirting factors for multiple conductors in a raceway, the correction factors for ambient temperature, and the requirements for conductors connected in parallel. The service entrance conductors must be sized to carry the calculated load, and the service overcurrent protection device must be sized to protect the conductors from overload and short circuit. If the load includes motors, the motor conductors, overload protection, and short circuit protection must be sized in accordance with NEC Article 430. If a transformer is used, the transformer must be installed in accordance with NEC Article 450, and the transformer overcurrent protection must be sized to protect the transformer from overload and short circuit. To provide a more comprehensive understanding, let's consider a detailed example of how to determine the maximum service amperage allowed for a 480 volts, three-phase service, taking into account various factors such as conductor size, insulation type, installation method, ambient temperature, and the presence of multiple conductors in a raceway. Assume that we need to supply a 480 volts, three-phase service to a building with a calculated load of 800 amps. The service entrance conductors will be installed in a raceway, and the ambient temperature is 35 degrees Celsius, 95 degrees Fahrenheit. We will use THHN copper conductors. Our goal is to determine the minimum size of the THHN copper conductors required for this service. Firstly, we need to consult NEC Table 310.15b16 to determine the ampacity of THHN copper conductors. According to this table, a 750 kc male THHN copper conductor has an ampacity of 700 amps at an ambient temperature of 30 degrees Celsius, 86 degrees Fahrenheit. However, since the ambient temperature in our example is 35 degrees Celsius, we need to apply a correction factor to the ampacity. Secondly, we need to consult NEC table 310.15 bone to determine the correction factor for an ambient temperature of 35 degrees Celsius. According to this table, the correction factor for THHN copper conductors at 35 degrees Celsius is 0.91. This means that we need to multiply the ampacity of the 750 kc mil THHN copper conductor by 0.91 to account for the higher ambient temperature. The corrected ampacity of the 750 kc mil THHN copper conductor is 700 amps times 0.91, which equals 637 amps. This is less than the required 800 amps, so we need to consider using multiple conductors in parallel. Thirdly, we need to determine the number of parallel conductors required to carry the 800 amp load. To do this, we divide the required load by the corrected ampacity of a single conductor. The number of parallel conductors required is 800 amps divided by 637 amps, which equals 1.26. Since we cannot use a fraction of a conductor, we need to round up to the next whole number, which is 2. This means that we need to use two 750 kc mil THHN copper conductors in parallel for each phase of the service. Fourthly, we need to consider the derating factors for multiple conductors in a raceway. According to NEC section 310.15b3a, if there are more than 3 current carrying conductors in a raceway, the ampacity of the conductors must be derated according to the adjustment factors provided in table 310.15 colon. In our example, we have 6 current carrying conductors in the raceway, 2 conductors for each phase. Therefore, we need to apply a derating factor to the ampacity of the conductors. Fifthly, we need to consult NEC table 310.15 colon to determine the derating factor for 6 current carrying conductors in a raceway. According to this table, the derating factor is 0.80. This means that we need to multiply the corrected ampacity of the 750 kc mil THHN copper conductor by 0.80 to account for the presence of multiple conductors in the raceway. The derated ampacity of the 750 kc mil THHN copper conductor is 637 amps times 0.80, which equals 509.6 amps. This is the actual ampacity that each of the two 750 kc mil THHN copper conductors can carry in our installation. Sixthly, we need to verify that the 2 parallel conductors are sufficient to carry the 800 amp load. The total ampacity of the 2 parallel conductors is 509.6 amps times 2, which equals 1019.2 amps. This is greater than the required 800 amps, so the two 750 kc mil THHN copper conductors in parallel are sufficient to carry the load. In summary, to supply an 800 amp 480 volts 3-phase service in an ambient temperature of 35 degrees Celsius with the conductors installed in a raceway, we would need to use two 750 kc mil THHN copper conductors in parallel for each phase. This example illustrates the importance of considering all of the relevant factors when determining the maximum service amperage allowed for a particular installation. It is essential to consult the NEC and to perform a thorough load calculation to ensure that the service entrance conductors are properly sized and that the electrical system is safe and reliable. Now let's consider another scenario to further illustrate the complexities of determining the maximum service amperage allowed by the NEC. In this scenario, we have a 480 volts, 3-phase service that supplies a large industrial facility. The calculated load for the facility is 1200 amps. The service entrance conductors will be installed in underground duct banks, and the ambient temperature is expected to be relatively stable at 25 degrees Celsius, 77 degrees Fahrenheit. We will use XHHW-2 copper conductors, which are known for their high temperature rating and suitability for underground installations. Firstly, we consult NEC table 310.15b16 to determine the ampacity of XHHW-2 copper conductors. According to this table, a 750 kcmil XHHW-2 copper conductor has an ampacity of 760 amps at an ambient temperature of 30 degrees Celsius, 86 degrees Fahrenheit. Since our ambient temperature is lower than 30 degrees Celsius, we can potentially increase the ampacity of the conductor. Secondly, we consult NEC table 310.15b to determine the correction factor for an ambient temperature of 25 degrees Celsius. However, this table only provides correction factors for temperatures above 30 degrees Celsius. For temperatures below 30 degrees Celsius, we can use the formula provided in the notes to the table to calculate the correction factor. The formula's correction factor equals the square root of T2 minus Ga divided by T2 minus tone, where T2 is the maximum conductor temperature rating, Ta is the ambient temperature, and tone is the reference temperature from the table. For XHHW-2 conductors, the maximum temperature rating T2 is 90 degrees Celsius, 194 degrees Fahrenheit. The reference temperature tone is 30 degrees Celsius, 86 degrees Fahrenheit. Plugging in the values, we get correction factor equals the square root of 90 minus 25 divided by 90 minus 30, which equals approximately 1.8. This means that we can multiply the ampacity of the 750 kcmil XHHW-2 copper conductor by 1.8 to account for the lower ambient temperature. The corrected ampacity of the 750 kcmil XHHW-2 copper conductor is 760 amps times 1.8, which equals 820.8 amps. This is still less than the required 1200 amps, so we need to consider using multiple conductors in parallel. Thirdly, we need to determine the number of parallel conductors required to carry the 1200 amp load. To do this, we divide the required load by the corrected ampacity of a single conductor. The number of parallel conductors required is 1200 amps divided by 820.8 amps, which equals approximately 1.46. Since we cannot use a fraction of a conductor, we need to round up to the next whole number, which is 2. This means that we need to use two 750 kcmil XHHW-2 copper conductors in parallel for each phase of the service. Fourthly, we need to consider the derating factors for multiple conductors in a raceway. Since the conductors are installed in underground duct banks, we need to consult NEC section 310.15c and the associated tables to determine the appropriate derating factors. The derating factors for underground duct banks depend on the number of conductors in the duct bank, the spacing between the conductors, and the thermal resistivity of the surrounding soil. For this example, let's assume that the derating factor for our installation is 0.85, based on the specific conditions of the underground duct bank. Therefore, we need to apply the derating factor to the corrected ampacity of the conductors. The derated ampacity of the 750 kcmil XHHW-2 copper conductor is 820.8 amps times 0.85, which equals 697.68 amps. This is the actual ampacity that each of the two 750 kcmil XHHW-2 copper conductors can carry in our installation. Sixthly, we need to verify that the two parallel conductors are sufficient to carry the 1200 amp load. The total ampacity of the two parallel conductors is 697.68 amps times 2, which equals 1395.36 amps. This is greater than the required 1200 amps, so the two 750 kcmil XHHW-2 copper conductors in parallel are sufficient to carry the load. In summary, to supply a 1200 amp, 480 volts, three-phase service to an industrial facility with the conductors installed in underground dust banks and an ambient temperature of 25 degrees Celsius, we would need to use two 750 kcmil XHHW-2 copper conductors in parallel for each phase. This example highlights the importance of considering the specific installation conditions and the properties of the conductors when determining the maximum service amperage allowed by the NEC. It also demonstrates the need to consult the relevant NEC tables and sections to ensure that the electrical system is designed and installed in accordance with the code.